Welcome back, AP Statistics students. Mr. Eicher here, looking at mock exam number 4. Question number 1. This was a question from several years ago that I added some parts. I think it's interesting, this question about chest compressions versus, or in addition to mouth-to-mouth resuscitation. Over the years as a teacher, I've had to get CPR training, and it seems like the requirement has gradually changed. And indeed, now chest compressions are almost the totality of what you do in CPR. Um, Whereas when I first started teaching, it seemed like it was about 50-50. You do chest compressions half the time and mouth-to-mouth resuscitation the other half the time. But now it's mostly chest compressions. So in the 1990s, study was done. And we have some data here. We have null and alternative. We have a p-value provided. First question is explain how the design of the experiment will address replication. I wanted to write a question that reminded you, so we could review what replication is and what's the benefit of replication. So replication in statistics is mainly, you don't want just one person in a treatment group. It might seem like an obvious thing to you, but it's really important not to have one person in a treatment group. So to explain that, design addresses replication by assigning multiple patients to each treatment. That ultimately is what replication is. Replication is an experimental design requirement. So some other experimental design requirements. You not only want replication, but you want some kind of comparison. You don't want to just have a study where you're doing CC alone and you're not comparing it to something. So that comparison could be like a placebo or a control group, inactive treatment or something, but you do have to have some kind of comparison. You need to have control. So control for confounding variables or other things that might influence your response variable. And then you have replication. And you need random assignment of treatments. So comparing treatments, you want to randomly assign the treatments. You want to control for other factors that you can control for. You're hoping that the random assignment will equally distribute the things that you can't control for. And then you need a lot more than just one person per treatment group. So that's what we have. We have multiple patients in each treatment group. And I've included, because sometimes it's really good to include context in AP statistics if you haven't learned that yet. Replication is important. So what's the benefit of replication? Replication is important to estimate the natural variability of survival within each group. The estimate of natural variability is needed so that the survival rates for the two groups can be compared. A treatment group with only one patient does not allow us to compare treatments effectively. So this whole talk about natural variability, if you just have one patient in a treatment group, then there's way too much variability for that one patient. You need more and more and more and more and more patients so you can kind of get an idea of the actual effectiveness of the treatment. So you imagine if I said like, hey, I want to show you a dot plot of how much Major League Baseball players make. There you go. That's really unhelpful. It's unhelpful because we don't have a scale. Let's say our scale is like 1 million to 20 million. Okay, so I guess they make a lot of money. But one dot isn't enough to see the distribution of the variable. We would need a lot more dots. So let's say we had a shape like this. Now that gives you a much better idea of what the distribution of Major League Baseball salaries looks like. Replication is the same idea. You don't want to have, okay, let's say survival rates. Yes, no, put no over there. There we go. So survival, 1 survived. We need a lot more than that. So let's say we did this. Okay, that gives us a better idea of survival rate. We got 5 out of 6. That's pretty good. So that's the idea of replication. You want to see the distribution of the variable And to be able to see a distribution, you need a lot more than one dot. You need a lot more than one patient. So that's replication. Construct an appropriate graphical display. I've given you two options here. Now, we just learned, after I made this exam, we learned that you won't have to do any graphs, make any graphs. So maybe what we could do is review how would you talk about graphs like this. But we have a segmented bar graph. We have one of my favorites, a mosaic plot. Remember, a mosaic plot, the width, this width, shows you that there were more in that treatment group, slightly more, not too many more, compared to this width, which is a little bit thinner. But otherwise, the heights of these bars, those heights are the exact same as what you'd get on a segmented bar graph, these heights. So if you were given a segmented bar graph like this and maybe asked to describe what you see, do not do socks. No. You only do socks with quantitative data. This is categorical data, right? These are yeses, yeses, and these are no's. Those are not numbers that you average. Those are numbers that you could, count and find a percentage of. So these are counts, and proportions are percentages. That's categorical data. No units. So how would you describe this? Well, you just describe what you see. What do you see? What do you see? What do you notice? Well, what I see is the CC alone has a slightly higher survival rate than CC plus MMR. Typically, I encourage you to do 2 or 3 comparative statements. The comparative statement being, I said, higher. It's a comparative statement. Now, with only 2 bars and 2 levels of our factor, we can't really say too much more. I mean, I guess you could say CC plus MR had slightly higher nose. That's kind of the complement of what we just said. But either way, the question as it stands is construct an appropriate graphical display, which this year you won't be asked to do that. What's the name of the appropriate test to test these hypotheses? That would be a two-sample z-test for a difference in proportions. Now we call it sample, but really it's like 2 groups because we didn't really have a random sample, but we are putting all of our patients, all of our subjects into one of 2 groups. So this 2-sample z-test is really a 2-group z-test. If you're familiar with calculator talk, this is a 2-prop z-test, but again, on the exam this year, you probably won't have to be finding z-scores and p-values with your calculator. Question D. The test resulted in a p-value of 0.0761. Interpret the p-value in context. On the previous video from mock exam 3 FRQ number 2, I think we reviewed that, but we'll review it again. So we have, assuming the survival rates are the same. So this is assuming the null to be true. We have context. There's a p-value, included that we observe a difference in proportions. This I had to calculate from the given information, but that's our statistic, or less, and that's our direction. So we have the 4 components. This is our statistic, and plus the direction of that statistic. Next, based on the p-value, what conclusion would you make? We have, since the p-value is greater than alpha, we have a statement about the null. We fail to reject. We don't have evidence, so mention evidence. And then we have the alternative in context. So here's our null comparison. Here's our evidence that we mentioned. Here's our alternative in context. And then this is our p-value compared to our alpha level. So those would be the components that you would need. I'll also mention, just throw out, similar to the ones in the study, we include that because we didn't random sample. We didn't sample randomly. So we can't really generalize to people beyond the people in this study, since we can't infer to a population without a random sample. And then lastly, I wanted to review type 1, type 2 errors. So what type of error might this have been? Since we fail to reject, this would be a type 2 error. And what's a possible consequence? We might have made a type 2 error where we didn't find convincing evidence for the effectiveness of CCC alone. But in reality, CC alone does produce. So I like this in reality, so I know what's the reality of the situation. And a consequence is that medical professions could be using a more effective approach, CC alone, to produce higher survival rate, but sadly, they're missing out because they didn't find evidence that it works any better. And another consequence is it's leading to a greater loss of lives. So type 2 error would be something that we'd want to avoid here. And if we want to avoid type 2 error, we don't want to miss out on effective treatment. If we want to avoid type 2 error, something we would talk about is we'd want to increase the power of the significance test. So the 3 ways, just to review that, the 3 ways to increase power. You can increase your alpha level, and increasing your alpha level allows you to reject the null more easily. So then you'll be more likely to find a treatment that is effective. Another thing you could do is increase your sample size. If there really is a difference between the two groups, the bigger your sample size, the more easily you'll find it. Also, it decreases your sampling variability. And then lastly, your effect size. If your effect size increases, then that will also increase the power of your significance test. So you could be asked about power and describing what power is, interpreting what power is, ways to increase the power. Thanks for watching this video. If you found that it was helpful, please give me a thumbs up below. And again, thanks for all your hard work in reviewing for this AP exam. Good luck.